Hi, class. So this is our third unit that we're entering this week with this lecture. We're going to start chapter 16. The next chapter we'll cover is 17. 16 and 17 are about energy changes that occur in chemical reactions. This is an extension of what you learned previously in chapter 5 on thermodynamics. So let's get started. I'm going to share my screen, PowerPoint. And we'll start on chapter 16, thermodynamics. It's about thermodynamics applied to chemistry, so we call that thermochemistry. It's about the energy changes that occur in chemical processes. In this chapter, we will learn what makes processes spontaneous from a thermodynamic explanation. We will define entropy and learn what it is. And also in this chapter, we will introduce two new laws of thermodynamics, the second and third laws of thermodynamics. Previously, the first law was introduced in chapter 5, and that will be the first thing we'll cover in this lecture, is just a review of the first law of thermodynamics. Lastly, we will learn what free energy is. The learning objectives for chapter 16 follow on what we're going to follow these topics that we're going to cover. First is to understand what entropy is and isn't, and have the ability to predict the change in entropy for chemical and physical changes. We will use the scale for entropy and its properties as a state function to quantitate the amount of entropy change to a system, to the surroundings, and to the universe. Lastly, we will learn how to use the thermodynamic state function Gibbs free energy to calculate spontaneity of a chemical or physical change. Today's lecture will focus on chapter 16.1 and 16.2 with the objectives to be able to distinguish between spontaneous and non-spontaneous processes, and be able to describe the dispersal of matter and energy that accompanies certain spontaneous processes. Lastly, we will work on worksheet 22 at the end of this lecture, so you might want to have it handy for this lesson. So as I said previously, this builds on what you learned in chapter 5 about chemical thermodynamics. And specifically in chapter 5.3, you learned about the first law of thermodynamics and internal energy. Many of the same principles will be applied in this chapter. The first law is defined in many ways, but this is one way you can describe it, that energy cannot be created or destroyed. And we use this principle to solve many chemical problems previously. Secondly, because energy cannot be created or destroyed, the total energy in the universe is constant. However, it can be converted from one form to another, and it can flow into and out of a system. This slide shows another statement of the first law in terms of the change in internal energy of a system. So what is internal energy? Every system contains internal energy, that is determined by the state of the system. Further, internal energy is called a thermodynamic state function. Later in this chapter, we will encounter other thermodynamic state functions. Ooh, that's a mouthful. But before we go further, I want to talk about what is meant by the state of a substance. Understanding what state means is important. In this context, state refers to the temperature, the pressure, the volume, and the amount, and the type of the substance, that is the chemical formula. So temperature is usually given in Kelvin. So it's always in Kelvin when we're talking about thermodynamics. Pressure is atmospheres. The volume, which specifically applies to gases, would be in liters, and the amount would be in moles. Once the state of a system, and the system is the chemical system, has been established, the state functions can be defined and quantified. Thermodynamic state functions like internal energy only depend on the initial and final states. Recall that thermodynamic quantities are specified at standard state conditions. You've probably heard that before, and especially back in chapter 5, talked about standard state conditions, and for gas laws, we talked about standard state conditions. Those are where the temperature is 0 degrees C or 273 K, pressure would be 1 atmosphere, and the quantity would be 1 mole of substance. So the change in internal energy can be determined and is shown in this equation as the heat flow represented by Q and the workflow represented by W, both into and out of the system when a change occurs. So in this slide is a schematic, if you will, or a visual representation of the change in internal energy. It illustrates the heat and workflow into and out of the system. So if the heat and work goes out of the system, the sign would be a minus Q for heat, minus W for work. If it goes into the system, the signs would be positive. In chapter 5.3, a state function called entropy was introduced. It is represented by the symbol H and is defined by the sum of the internal energy and work. In this formula, pressure volume work is what's represented, which is the usual kind of work found in chemical systems, pressure volume work. Only changes in enthalpy can be determined. This slide shows that for chemical systems at a constant pressure, which is pretty common, the enthalpy or the delta enthalpy, the delta H, is equivalent to the heat change in the chemical process. So you look at the bottom, this is derived. This is the derivation. You don't have to worry about the derivation. But this is how we usually think of enthalpy, as a heat change in the chemical process. This occurs when the system is at constant pressure. Excuse me. So remember that the change in enthalpy, or the delta H for a chemical reaction, can be calculated from the standard enthalpies of formation of products minus reactants. So it's the end minus, it's the value of the enthalpy at the end of the reaction minus the value of the enthalpies at the beginning, which would be the products minus the reactants. This is called Hess's law. And we'll be using it later in this chapter when we talk about entropy and free energy. I want you to also remember that a negative delta H for a chemical change represents an exothermic reaction, and that heat is lost to the surroundings, and that a positive delta H represents an endothermic reaction, and heat is absorbed from the surroundings. Remember when we talked about equilibrium, if it was exothermic, we could visualize the heat as a product. And if it was endothermic, we would visualize heat as a reactant. So that's also useful to remember. So let's summarize just what we know about enthalpy. These are some rules that apply to all thermodynamic state functions. Now, enthalpy is a state function. We're going to learn about two more in this chapter. It's an extensive property. An extensive property, if you recall, means that it depends on how much of a substance there is. When we talk about standard enthalpies, we're talking about the amount of enthalpy in 1 mole of substance. But if you have 2 moles, the enthalpy is doubled. Okay, that's what extensive means. The delta H for reaction is for the reaction as written. So if you multiply all the molar quantities in the reaction by 2, the delta H is multiplied by 2. So this again is part of Hess's law. The delta H for reaction in the forward direction is equal in size but opposite in sign to the delta H for the reverse reaction. Okay, so if it's exothermic for the forward reaction, it would be endothermic for the reverse reaction, and equal in magnitude. Fifth, the delta H for reaction depends on the state of the reactants and the products. And this is very important for entropy as well. So remember the state, in this case, when we talk about state, we're talking about whether the phase, whether it's a gas, liquid, or solid. But whether a substance is a gas, liquid, or solid depends on those other variables in a system like temperature and pressure. Those determine what state or phase the chemicals are in. So in this chapter, we're going to explore why some of the chemical and physical reactions are spontaneous and why some are not. But first, let's define spontaneity. It's a process that occurs naturally at a given temperature and pressure without influence of any outside force. There are lots of examples of spontaneous processes. For the one shown here, where we have hydrogen reacting with oxygen with a little spark to produce water, is very spontaneous. If you've ever seen this happen, you know that it produces heat, light, and sound energy, and happens in an instant. It's really fast. All it takes is a spark. Static electricity will make this go. It seems probably obvious that a process that does not occur spontaneously is called non-spontaneous. But maybe not so obvious is that non-spontaneous process can be forced to occur by adding energy or an external force. For example, we know water naturally flows downhill, but if you put it in a pipe and add a pump and a motor, you can make it go uphill. Let's take a closer look at spontaneous processes. First, some are fast and some are slow. So this slide we say it's important not to confuse spontaneous with fast. This is called the kinetic versus the thermodynamic stability. Many processes are kinetically slow, which we'd call that stable. Slow would be stable, and have the appearance of being stable. So I just want to kind of clarify some terms, just to note that stability equates with being non-spontaneous. Non-spontaneous or stable means that the system is in equilibrium. We just finished talking about equilibrium. Equilibrium is where the amounts of the materials, the system is not changing, okay? So unstable, conversely, unstable equates to a spontaneous change. That means the system is changing. So here's a couple of examples of spontaneous processes that occur at different rates. We've got two examples here. So we remember radioactive decay and half-life. Radioactive decay is spontaneous, but different nuclides decay at different rates. Some nuclides decay extremely fast and others extremely slow. Remember, when we describe the rate of change, this speed, studying the speed, is called chemical kinetics. Well, in any process, you have to consider both of these, the thermodynamic stability, and the kinetics, how fast it's going to go. The process is thermodynamically spontaneous, but kinetically slow. The change will not be very fast and difficult to observe. It's like this first radionuclide, U-238. It doesn't appear to be decaying at all, but it is thermodynamically. These things decay spontaneously. We know that. But if you just looked at the amount of it over time, especially over your lifetime, it wouldn't even change. It's going so slow. So another example is the conversion is the thermodynamic stability of between graphite and carbon, two different forms of diamond and graphite, two different forms of carbon. So it turns out that graphite is actually more stable than diamond. Graphite is thermodynamically more stable than diamond. So what does that mean? That means that diamonds are thermodynamically will spontaneously change into graphite. But the reason why you don't notice this is because the kinetics for this change are very, very slow. But you can speed it up if you increase the temperature. So you don't want to put your diamond in a fire and see what happens to it, because it'll turn black and change into graphite. Okay, keep your diamonds out of the flames. So an early observation was that often spontaneous process occurred with the release of heat, that they were exothermic. Although there are many examples of this, not all spontaneous changes are exothermic. We talked about one spontaneous process. The reaction between hydrogen and oxygen produces a lot of heat. Right, and there are many reactions like this. But a very common example that is not thermodynamically, or that does not produce heat, is just ice melting at room temperature. This is an endothermic change. We know that. We know that heat has to be absorbed by the ice in order to melt it. On the other hand, ice at minus 10 degrees does not melt. So after studying this chapter, this observation will be understood from the thermodynamic viewpoint. Let's examine one spontaneous process where a gas confined to one of two connected chambers spontaneously flows into the empty chamber when the valve is open and fills both containers equally. There are three ways given in the book to explain this observation. First, gas molecules contain energy and are initially confined to one flask, but when the valve is opened, the energy in the gas spreads out with the gas molecules, and this spreading out of energy is a spontaneous process. Second, the gas molecules are always in motion, so there's greater probability that the gas will occupy both flasks rather than all the gas staying on one side or the other side. The change will spontaneously occur to the greater probability state. And we have some exercises, a couple of problems in the worksheet that illustrate that. And there's a good illustration in your book as well. The third explanation for this spontaneous change is due to the greater number of microstates. That is, when the valve is open, there are more places for the molecules to occupy, to reside. An increase in the number of microstates is spontaneous. So all of these are consistent with spontaneous process. So another thermodynamic property of matter, in addition to energy, needed to be defined. This property is called entropy. It's an increase in entropy through a more uniform dispersal of matter and energy is also a driving force for spontaneous processes. So remember previously we said that a negative entropy or an exothermic entropy change was a driving force for spontaneous processes. Well, there's another one called the entropy. An increase in entropy is a driving force for spontaneous processes. This is important. You need to remember that. So let's explore more about entropy. It's chapter section 16.2, where we'll explain the relationship between entropy and the number of microstates and be able to predict the sign. We'll look at how we can predict the sign of an entropy change for a chemical and physical process. So like enthalpy, entropy is a state function. It only depends on the initial and final states. So we can calculate the change in entropy as shown in this slide. The delta S equals the final entropy minus the initial entropy in a process. And spontaneity, as I mentioned before, is favored by an increase in entropy. So if the delta S is positive for a chemical change or chemical process, that's going to favor a spontaneous process. So one measure of the increase in entropy is an increase in the number of microstates. So Ludwig Boltzmann came up with this simple equation for calculating entropy from the number of microstates. Notice that the units of entropy are joules over K. So it's energy divided by temperature. We'll see this again. When the number of microstates increases, entropy increases. And as previously stated, an increase in entropy favors spontaneity. The opposite is also true. A decrease in entropy favors non-spontaneity. Spontaneity, aka stability. So let's look at a simple model system that consists of two particles and two boxes. The number of microstates possible is 4. This is the formula for how you calculate microstates. W is the number of microstates. It's the number of boxes, little n, to the power of n, which is the number of particles. So in this case, we have 2 boxes and 2 particles. So the number of microstates is 4. So here are the 4 microstates. So we have 2 particles in the left box. That's 1 microstate. We have 2 particles in the right box. It's another microstate. So let's see here, left box, right box. And we have 2 boxes, or 2 microstates with 1 particle in each box. So the most probable situation is 1 particle in each box. The chances are 2 out of 4 for 1 particle in each box, instead of just 1 out of 4 for 2 particles in the left box, 2 particles in the right box. So statistically, this is a statistical treatment of entropy. Statistically, these particles spreading out is the most favored state. So that's why if you have both particles on one side and you open up a path between the 2 sides, they're going to spread out. That's a spontaneous change. So this applies to our previous picture of 2 glass bulbs, or gas confined on one side of 2 bulbs separated by a valve. When you open the valve, it spontaneously spreads out into both sides. There's just a lot more particles, that's all. So the delta S in this case would be positive. Delta S for the final state on the right side would be higher, the entropy for the state on the right side is higher than entropy for the initial state. So the delta S is greater than 0, which indicates this change will be spontaneous. If that favors a spontaneous change. So let's look at some considerations or conditions that favor increased entropy. First, you must consider the phase of the substance. We talked about phases before. We talked about enthalpy. Well, the entropy, the phase, is also very important. The entropy of a solid is less than the entropy of a liquid, which is less than the entropy of a gas. Second, the temperature of the substance. The higher the temperature, the greater the entropy. I'm going to show you a graph that illustrates this. Third, the type and number of particles. The more complex the molecule, the greater the entropy. The greater the number of particles, the greater the entropy. And remember, we can equate the number of moles to the number of particles. So in the system, if you're producing more moles of something, especially in a gas reaction, that's going to have increased. Also, mixtures have greater entropy than pure substances. There's just more ways to combine the more microstates, if you will, when you have a mixture. So here's a graph that shows what's going on with temperature. So in this graph that's very narrow, this is the fraction of molecules with certain, the x-axis or the y-axis is the number of molecules, you could say. The x-axis is the kinetic energy of those molecules. So at a low temperature, we just have a very few molecules over a very narrow, we have lots of molecules, I should say, over a very narrow range of energies. if you go to higher temperatures, you have more molecules spread out over a wider range of energies. So instead of having a lot of molecules over a small range, you have of energies, you have a lot of molecules, same number of molecules over a wide range of energies. And that spreading out of energy, remember, that favors increased entropy. So that's the end of the lecture. I'm going to stop the share. I'm going to go to the worksheet now. So let's look at this worksheet. So this is worksheet 22. The first page has to do with statistical entropy, and the second page has to do with predicting changes, whether entropy will increase or not. So there are three problems on statistical entropy. So I'm going to do the first one was shown in the slide, in the PowerPoint slide. This is what we looked at. It was the two box, left side box, right side box, and two particles. We said the conditions are you can have two particles in only the left side. So here are the microstates. This is the first microstate, second microstate, third microstate, fourth microstate. So if you have the situation where you have just two particles in the left side, or two particles on the right side, or one particle on the left and one on the right, and then these particles are not the same. They're individual particles, so we can switch them and put the B particle in the left and A particle in the right. So the chances of having one particle on both sides is 2 out of 4 chances, which is statistically more likely than having the particles exist on one side or the other. So I'm going to do this other condition where we have 3 particles. So we have 2 boxes. And remember the number of microstates. Let's see, I'm going to write it down here. The number of microstates is equal to the number of boxes carried to the power of how many particles you have. So that means we have 8 microstates here. So these are the 8 microstates. So I just put rows for the 8 microstates. So in this worksheet, I filled in the real easy one. I put all 3 particles on the left side. That's the first microstate. And I put all 3 particles on the right side. So those are 2 possible microstates. But the chance of all 3 particles on the left side is 1 in 8. The chance of all 3 particles on the right side is also only 1 in 8. So that's not too great. So let's fill in the rest of the microstates and see what it looks like. So we can have 2 particles on the left and 1 on the right. So let me do those. So we have, or we can switch these particles. 1 on the left and 2 on the right. Oops, AB. Sharp my pencil here. You can have A, C on the left and B on the right, or B on the left and AC on the right. You can have BC on the left and A on the right, or we can have A on the left and BC on the right. So those are all the possibilities. So what does it look like? So because we have an odd number of particles, they're never going to be equally distributed, but it looks like the probability of having 2 particles on the left and 1 on the right, so 2 on the left and 1 on the right, is the chance of 1, 2, 3, and 8. So I'll fill that in there. 2 on the left, 1 on the right is 3 and 8. On the other hand, if we have 1 on the left and 2 on the right, that's also 3 and 8. So those are equal. So that's probably what would happen in this situation, is that you're going to have 2 on one side and 1 on the other, or vice versa all the time. So that's what would be favored. So what I'd like you to do is to work out the situation for the microstates for 4 particles in 2 boxes. So I've filled out a chart here for you already to make it easy. This would be W is going to equal 2 to the 4th, which is going to equal 16. So there should be 16 microstates here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I think you probably already know that what we hope will turn out is that the most likely situation, what we would expect is that there'll be 2 particles on the left side and 2 on the right side. That should be the most favored situation. So if you fill out this chart, that's what you should be looking for. So you try it out, see if you can fill that out yourself. If you have any questions, let me know. Well, let's look at the second page here. Second page is a little different. This is looking at some of the factors that cause increased entropy. And this is qualitative. We're not going to do any calculations yet. That'll be for later. But right now, let's look at these situations. I'll do every odd one. I'll do the odd ones and you do the even ones. So I'll circle the ones that I want you to do, 2, 4, and 6. And I'm going to do 1. I'll look at 1, 3, and 5. So in the first case, we're going from a solid to a gas. Well, a gas, a couple things. A gas is going to occupy more space, and that means there's a lot more microstates. But just in basic principle, when you change from a solid to a gas, the delta S is going to be greater than 0. So that will be spontaneous. So I'll just put spontaneous there. All right? Because we're going from a solid to a gas. In the second case, we have a solid iron on the left, gaseous oxygen, producing iron oxide, which is a solid. So we go from a system with a solid to a solid, which probably doesn't change it too much, except the solid on the right is a little more complex, which means it would have a little bit higher entropy. But we're going from a gas on the reactant side, and there's no gas on the other side. So that gases have tremendous entropy. And so the delta S in this case, since we don't have any gas on the product side, the delta S is going to be less than 0 because we lose the gas. There's no gas anymore. The delta S will be less than 0. Let's look at number 5. So number 5, we're going from a solid. Looks like we're adding that solid to water, and the ions separate. So you get dissociation. Well, if you get dissociation, that's going to be dispersal of matter, right? So it goes from a solid crystal into a dispersed form. And also, you're adding it to water. So you're making a mixture. So both of those, first of all, so we can predict that delta S is going to be greater than 0 because we've produced a mixture which has greater entropy than a pure substance. And we have dissociation of the ions. Okay, so I'll let you do the even numbered ones, all right? If you have any questions, let me know. And that's the end of the lecture. So I'll just sign off for now. And the next lecture will be on chapter 16.3. Goodbye.